Hello, and welcome to Lesson 3 of the Business Analytics Foundation with R Tools course offered by Simplilearn. After completing this course, you will be able to get a basic introduction to R, understand exploration of data, explore data using R, visualize data using R, understand diagnostic analytics, implement diagnostics analytics using R, understand the concepts above with the help of case studies. Let's start our lesson with a basic introduction to R. R has become one of the most popular tools for data mining. Let's see why and also gain some basic knowledge on R. R is a freely available programming language for statistical computations and graphics. It is published under the GNU Public License. It is mainly used in the fields of data mining and statistical analysis. Out of its various applications, it includes time series analysis, linear modeling, and nonlinear modeling. The main advantage of using R over other such tools for data mining is its active community, the built-in packages, and the package contributions by the members of the community. Another reason for its popularity is that R needs very little programming knowledge. You can download R from its official website, r-project.org. The website has instructions on how to download and install R and the basic machine requirements. RStudio is an IDE for programming in R that is freely available. It is completely optional for you to download RStudio. The programming in the following chapters will be taught using the R command line prompt. If you are using RStudio, you can type in the same commands as shown in the chapters. Finally, you are strongly encouraged to check the community forums on R as you go through this lesson, to answer basic questions and to explore the different functionalities of R. In the next slide, let's start with a very basic introduction to the commands in R. Getting into the specifics and statistical analysis in R, listed here are a few important commands that would be used throughout the course. To use a particular package, the install.packages function is used. This installation needs to be done only once. Once installed, the functions can be loaded into the current session by calling the library function. R comes with a set of built-in sample data sets, which we would be using in our lessons. This data can be loaded using the data function, and the syntax is data of dataset name. To use external data, the read function is used. The write function writes data from the R session to a file. R's default directory is the user's documents folder. It can be verified by using the getWD function. To change the working directory, use the setWD function with the full path name as the argument. In case the working directory is not set, the full path name needs to be specified for read and write functions. For example, read.csv of c:/r tutorials/sample-data.csv. Note that R uses the / for specifying directories. The assignment operator in R is different from the equal to operator. To assign a value to a variable in R, use the lesser than dash symbol. For help on any function in R, type question mark followed by the function name to open the R help text. If you are using R, the help text will open on the default browser. In the next slide, we will look at the basic exploration using R. Before getting into the functions and commands for data exploration, let's look at how data is stored in R. The data in R is stored as data frames, which are a tabular representation of the rows and columns. There are other types of data as well, including table, matrices, vectors, and single values. In our course, we will primarily use data frames and time series data in the later chapters. In the slide, you can see a sample data frame. The IRIS dataset is a very popular, commonly used dataset introduced by Sir Donald Fisher. The data contains 150 entries belonging to 3 different species and includes features such as sepal length and width, and petal length and width. The 3 species have 50 entries each, as shown in the data frame. Each row denotes a particular case, or in this context, features of a particular flower. The column denote the different attributes measured. In the next slide, we will look at different commands to view data. Let's start with basic commands to view data in R. Throughout this lesson, we will look at commands and screenshots of R that will display a sample output. You are encouraged to pause the video and try out the commands on your command prompt for better understanding. The IRIS dataset is loaded by default in R. To view the dataset, just type the dataset name on the prompt. To view the top few records, use the head function. The syntax is head of dataset name, comma, number of rows. The number of rows is an optional argument, and the default number of rows is 6. To view the last few records, the tail function is used. The syntax is similar to the head function. Tail of dataset name, comma, number of rows. In the next slide, we will look at commands to view the dimensions of data. Listed here are a few commands to view the dimensions of a dataset. Dim of dataset name gives a vector result of the number of rows followed by the number of columns. Encol of dataset name gives the number of rows, and nrow of dataset name gives the number of columns separately. Try these commands with the sample IRIS dataset. In the next slide, we will look at the attributes of the data frame. To view the column names of a particular dataset, type names of dataset name. To view all attributes, type attributes of dataset name. Given here is a snapshot of the 2 commands of the IRIS dataset. You can see that the column names are displayed as strings in the first output. Attributes displays the column names, row names, and the data type of the dataset. The class command is used to display the data type of the argument. The syntax for class command is class of variable name. For example, class of iris would be data.frame. To know the type of a particular column, type class of iris $sepal.length. The $ is used in referencing the columns of a dataset. In the next slide, we will look at viewing columnar data. To view data of a column, the following 2 notations be used. As mentioned in the previous slide, dataset $column name would display the particular column. Another way is to use a matrix form. That is, dataset of space, comma, column name. Instead of the column name, the column number could also be used. In this case, petal length is the third attribute, hence iris of space, comma, 3 would also give the same result. In the next slide, we will discuss viewing row-wise data. Similar to columns, data of particular rows can also be viewed using the square brackets. The format is dataset name of row numbers, comma, space, to display all columns, or dataset name of row numbers, comma, column name or numbers, to display particular rows of particular columns. You can see the screenshot for the subsets using square brackets on the iris dataset. Also note, if a single column or row is displayed, the output is in default vector form. This concludes viewing data and exploration in R. You are advised to try out all these commands on your R or RStudio for better understanding. Next, we will look at a video to illustrate the commands we have used so far. This video shows all the basic operations that can be performed on R and will help any layman to use R efficiently. We start off with one of the very basic operations that help us to load and install any package that is not pre-installed in the R workspace. Step 1. This operation is called install.packages, with the package name within double quotes. Step 2. A pop-up opens that asks for the server to which you should connect to download the package. Zero Cloud at the beginning is enough to download the package. Selecting that and clicking on OK downloads and installs the package. Step 3. Then the package needs to be loaded onto the workspace, which we do by using the library function. Once that is done, the features of the package can now be used for our purpose. Step 4. Next, we try to load a dataset that will be frequently used for all the analysis that follow. This is the iris dataset, and you load it using the data function. Data of iris loads the iris dataset onto the workspace. Step 5. Now we shall do some basic analysis on R. Just to note that before doing any analysis, it is safe to save the dataset onto the workspace that we try to use by using the attach function. So attach of iris will save the dataset onto the workspace. Step 6. Once done, we can remove it from the workspace by using the detach function. That is, detach of iris will remove the dataset from the workspace. Step 7. First, we load the dataset into a user-defined variable, say, my data, using the assignment operator less than dash, which is less than sign followed by a hyphen. We can also use the equal sign instead. Both work the same way. Step 8. Now that the data is loaded into the user variable, we can check the structure of the data using the head function. Entering head of my data returns the first 6 records of the dataset. Step 9. Now the screen is pretty full and we would like to clear it. A keyboard shortcut comes in handy at this point, and that is Control-L. which clears the screen of the current workspace. Step 10. Next, we look at how to check and change the current working directory. The function getWD returns the current working directory we are in, and the function setWD helps in changing the working directory, which we pass as argument to the function within double quotes. The next function that we are going to look into is the read function in R, along with the type of files that can be read. Step 1. Read.csv helps us to load a CSV file, the path for which we need to pass as argument to this function. We load the dataset stored in the file into a user variable, and then check the structure using the head function. Step 2. We can even make a data frame of this data by using the data.frame function and passing the red.csv as an argument, or we can even pass the user variable that stores the data as an argument. Step 3. Just like the head function, we have the tail function that shows the last 6 records of a dataset. Tail of the dataset returns those records. Step 4. We can display as many records by passing the required number as an argument after the dataset name. So, head of my data, followed by a comma, and then the number of records you want to view returns those records, many from the start of that dataset. Next, we check 4 more basic functions of R, namely dim, encall, enrow, and names. Step 1. The dim function returns the dimensions of the dataset. That is, the total number of rows and columns. Run the command dim of dataset name to get the required result. Step 2. The encall function returns the total number of columns, and the enrow function returns the total number of rows in the dataset. Run the commands encall of dataset name and enrow of dataset name to get the corresponding results. Step 3. Lastly, the names function returns the title of all the columns that are there in the dataset. As usual, run names of dataset name to get the column names. Data manipulation. Moving on to viewing row and column data, the following techniques are possible. Column data can be viewed in 3 different ways. First technique. Call the column name after the dataset name using the $sign. That is, dataset name $column name. Second technique. Call the column name as a matrix attribute of the dataset. That is, dataset name, then within the square brackets, enter comma, followed by the column name with double quotes. Third technique. This is similar to the second technique, with the difference that in place of the column name within the square brackets, we need to enter the column number. Row data can be viewed in the following way. Enter the row number, followed by a comma within square brackets after the dataset name. We can view multiple rows by entering the first and last row of our choice, separated by a colon. In the next slide, we will look at the summary functions. The summary function is a generic function in R that displays summaries of data or models. as we will see in later chapters. The syntax is summary of dataset. As shown in the screenshot, the summary function displays the minimum value, maximum value, mean, median, and first and third qualities of every numeric data. For categorical data, like species, it displays a table of the different values and their frequencies. The table can be displayed separately by giving table of data frame $column name. Look at the example. Table of iris $species displays a frequency distribution of the 3 different classes. Note that summaries for individual columns can also be obtained by using the summary function and giving the referenced column name as an argument. For example, summary of iris $sepal.length would display the results of sepal length column alone. In the next slide, we will look at a list of commands for the individual summary statistics. The summary function displays all the summary statistics for a particular data. Here you can see a list of commands to display individual summary statistics. The argument for each function is the column name for which the statistics is to be obtained. The commands are min to get the minimum value, max to get the maximum value, range to get the range of the data. That is, maximum minus minimum value. Mean to get the average value. Median to get the median or middle value. IQR to get the interquartile range of the data. That is, the difference between the first and third quartiles. SD to get the standard deviation. VAR to get the variance. In the next slide, we will look at ways to aggregate data in R. Next, we use the summary function of R to get an overall snapshot of the whole data set. Step 1. Summary of the dataset name returns the mean, median of each numeric column, and the frequency of levels of every categorical column. There are various other functions that can be used to separately analyze all the columns in the dataset. They are as follows. Step 2. Min. Min of column returns the minimum value in that column. For example, when we do a min of the sepal length column of the iris dataset, we get the value 4.3, which is the lowest value in the column. Step 3. Max. Max of column returns the maximum value in that column. For example, when we do a max of the sepal length column of the iris dataset, we get the value 7.9, which is the highest value in the column. Range. Range of column returns the range of values in that column. For example, when we do a range of the sepal length column of the iris dataset, we get 2 values, 4.3 and 7.9, which tells us that the values in the column lie between these 2 extremes. Step 5. Mean. Mean of the column returns the average of all the values in that column. For example, mean of sepal length returns the value 5.8433, which is the average of all the values in sepal length. Step 6. Median. Median of a column returns the central value of by position in that column. For example, median of sepal length returns the value 5.8, which is in the middle of all the values in that column. Step 7. IQR. The IQR of a column returns the interquartile range of that column giving us a sense of the difference between the upper quartile and lower quartile of the values of that column. IQR of the sepal length returns the value 1.3. Step 8. Standard deviation. The function SD is used to find the standard deviation in a column of the data set. For example, SD of sepal length returns the value 0.8280661. Step 9. Variance. To find the variance in R, we use the var function. So var of sepal length returns the value 0.6856935. Having finished all the basic statistical function in R, we now move to aggregating the dataset at hand. Aggregating the dataset is one of the few important data manipulation functions in R. Parameters that need to be passed into the aggregate function are formula for the aggregation, dataset used, and the type of aggregation. That is, a mean aggregation or a sum aggregation. Aggregation in R can be done using the aggregate function in two ways. The two ways differ only in the formula that is used for the aggregation. Step 1. In the first way, we do it across the dataset by a particular column. Like the iris dataset, we can aggregate across the dataset by species. Step 2. For this scenario, we enter the formula as dot tilde followed by the column name, which is species in our case. The enter data equals iris for specifying the dataset, and last give the type of aggregation, that is mean or sum. Step 3. In the second way, only the formula differs such that the aggregation is not done across the dataset, but only on the variables or columns used in the example. With this, we come to the end of the basic operations that can be performed in R, right from data viewing to data manipulation to basic statistics. Next, we'll focus on the visual aspects of R. In the next slide, we will look at the functions to visualize data in R. The aggregate function is used to group data values of a particular column. The compulsory arguments are the formula for aggregation and the function for aggregation. The first argument aggregates all the columns, as denoted by the dot symbol, grouped by the value of species. The next argument mentions that the data belongs to the iris dataset, and the last argument specifies that the aggregation should be done by averaging the values. You can see the result has 3 rows, one for each class, and the mean values for each column. The second command aggregates only the sepal length column by species, belonging to the iris dataset. In addition to the mean function, the sum function is a commonly used statistic in aggregation. You can see the other available functions by typing a question mark followed by aggregate to see the help content. Next, we will look at a video that illustrates summary statistics. Plot is a generic function used for plotting data in R. The function can be used to plot a variety of graphs on a variety of data, including data frames, time series, and even vectors. The plot function creates a scatter plot by default. Other plots can be created using the type attribute. You can check the help section for more details on the plot function. Shown here is a plot of iris data. On plotting the data frame, it creates a pairwise data plot for all the attributes in the data frame. In the next slide, we will look at a simple scatter plot. The plot function can be used to create scatter plots of one variable against another. For example, let us plot sepal length against species. We will use a few optional attributes of the plot function. Main, to specify the title of the plot. xlab, the x-axis label. ylab, the y-axis label. The function would now be plot of iris $sepal dot length, comma, iris $species, comma, main equals iris data, comma, xlab equals sepal length, comma, ylab equals species. The output plot is shown on the right. From the scatter, it is easier to notice the differences in the sepal length according to species. Next, we will look at pie charts. Pie charts are the simplest form of visualizing the numerical proportion of the different classes through the sectors of the circle. The pie function is used to create pie charts in R. The table function is used to create a frequency table, and then the pie function is called to create a chart of the table. The main attribute, as mentioned before, is used to specify the title for the chart. Here is an example chart showing the different species of iris data. The circle is divided into 3 equal sectors for the 3 species. In the next slide, we will look at bar charts. Bar plots are used to depict values in vertical manner, with the height being equivalent to the value that's being shown. For this example, we will use another built-in data set, U.S. Personal Expenditure. The data set is displayed in the table. It displays the personal expenditure data for categories across years 1940 to 1960. In R, bar plots can be created using the bar plot function. As with the plot function, the main, xlab, and ylab attributes can be used for labeling. This slide shows an example function to create a bar plot using the expenditure data, and on the right, the created bar plot is shown. In the next slide, we will create box plots. Box plots are used to show numerical data with their quartile ranges, also called a box whisker plot. The boxes show the interquartile region, with the middle line equal to the median. The whiskers show the lower and upper quartiles, and the points show the outliers. The box plots are very useful in detecting the outliers. In R, box plots can be created using the boxplot function. Let's see the example function displayed on the slide. The first attribute shows the features to be plotted. That is, sepal length against the species, the data, and the labeling information. On typing this into the R prompt, you will get a graph similar to the one shown on the slide. You can see that there is an outlier in the Virginica species. In the next slide, we will look at histograms. Histograms are used to depict frequency distribution data. R has a default islands data set that is best suited to create histograms. Once you are done with this slide, you are encouraged to try creating a histogram using the islands data. In R, histograms can be created using the hist function. The first attribute gives the vector or data frame to plot, and the usual labeling attributes can be used to label the plot. It can be seen from the plot that the sepal length is mostly concentrated around 4.5 to 6.5. For numerical data such as sepal length, the data is put into buckets and the histograms are created. This slide concludes data visualization. In addition to these attributes, plots can have other attributes such as X and Y axis limits, colors for points or bars or lines, etc. They can be found in the Help section for each plot. Next, we will look at a video that helps in understanding the different commands used in visualizing the data. Basic data visualization in R can be done using the plot function. Step 1. When we do a plot of the iris data set, a separate window pops up showing a scatter plot across each and every variable of the data set. Step 2. If we want a plot of any particular variable or set of variables, then we pass the variable or column names as argument to the plot function. For example, for plotting the sepal length across species, we give the sepal length and species as the arguments, separated by a comma. Here, the first argument is the x-axis argument for the plot, and the next argument is the y-axis. Step 3. Next, we can generate a pie chart in R using the pie function along with the table function. In our case, we use the species column of the iris dataset and pass it through the table function to get a frequency table of all the species, which is then used to generate the pie chart. So we enter the pie of table of species and get the pie chart as output. Step 4. Further, we use the bar plot function to generate the bar plot chart, and in our case, similar to the pie chart scenario, we enter bar plot of table of species to get the bar plot chart. Now, for the box plot function, we need to pass a formula specifying the variables that are required to be plotted. Say, for example, sepal length tilde species, and along with that we enter the data equals iris separated by a comma, and then try to generate the required box plot. Step 6. The final basic visualization function that comes to use is the histogram plot generated using hist function. The basic argument that needs to be passed is the variable that we want to plot. In our example, we just need to pass, say, the sepal length, and we get a histogram plot. We can fine-tune this plot by passing the main chart title, x-axis, titled, and y-axis titled using the main xlab and ylab arguments in the plot function. And this can be done in case of all other plots. In the next slide, we will look at a case study to understand what we have learned so far. Let's now take a banking-related data set as an example for doing data exploration. Officer David from the sales department has been asked to do a study on the overall performance of a bank by analyzing the bank loans. As part of the investigation, David has asked his colleague to categorize the loans as seasoned or bad loans with respect to age category. The following data categories have been captured: age group, total number of loans, number of good loans, number of bad loans, percentage of good loans, percentage of bad loans. In the next slide, we will have a look at the data. Here you can see a table of the bank loan data. As mentioned in the previous slide, the number of good loans and bad loans has been tabulated as per the age category. There are 15 categories of age in the table. Given the total number of loans and the number of good and bad loans, The percentage of good and bad loans has been tabulated. In the following video, we will look at different statistics and graphical visualizations for the data. Let us start by exploring the data. Since it is a preloaded dataset in R, we will not be using any read command. However, if you wish to save it to an Excel file, use the write.csv command. The write.csv command takes two arguments: the data frame name and the name of the file you wish to write it to. For example, .csv of empty cars, comma, motor trends car data .csv creates a file motor trends car data in the current working directory with the given data. Step 1. First, let us view the data set. Type empty cars to display the whole data set. We learned the concept of data frames earlier. Let us find the class of the data set in R. Type class of empty cars and hit enter. From the output, we can infer that the data is stored as a data frame. Step 2. Let us confirm the number of columns and rows in the data set. Type dim of empty cars. The output shows 32 and 11 separated by a space, implying that there are 32 rows and 11 columns. Step 3. Let us explore the data in detail. Use head of empty cars to display the first 6 rows. Though we already established the types of the variables, let us confirm it by looking at this data. We can see that VS and AM have either 0 or 1 values, and thus have been rightly classified as categorical data. The number of cylinders, gears, and carburetors has discrete numerical values, and the rest of the data are in continuous numeric format. Step 4. To look at all the types of cars, type attributes of empty cars and press enter. The first section gives the column names, which we have already discussed. The second section has row names, which consists of the model names of all 32 cars. Finally, the class of the variables displayed, that is, data frame. Step 5. Let us find what all values that the variable number of gears can take. Type empty cars $gear. All the values of the column are displayed. You can see that the values 3, 4, and 5 are repeated in the data set. Similarly, you can check the number of cylinders and carburetors too. Step 6. Suppose you would like to know the attributes of a particular car. For example, the Ferrari Dino. We will use the format to view the row data here. Type empty cars of Ferrari Dino and a comma within square brackets, and press enter. You can now see the attributes of Ferrari Dino displayed in a single row. Step 7. Now that we have explored the data, we will now look at summarizing to get some meaningful insights. Before doing this, let us first convert the data type for versus and AM to factor. They are numeric by default. To convert the data type, use the as.factor command. Type empty cars $AM equals as.factor of empty cars $AM. Do the same for the versus variable as well. Step 8. Getting into the summarizing part, as seen earlier, type summary of empty cars to display all the summary statistics. From the first section, we can infer that the maximum miles per gallon is 33.90, and the average is 20.09. The minimum miles per gallon is displayed as 10.40. Similarly, we can note the maximum, minimum, and other statistics for the rest of the numeric data. For the categorical data, the number of entries in each group or category is displayed. For example, from the AM column, it can be inferred that out of 32 cars, 19 are automatic and 13 are manual. Step 9. What if we need to know which car among the 32 gives the best mileage? The which.max function is used to return the index of the maximum value in the dataset. For example, type empty cars of which.max of empty cars $mpg and a comma. The which.max returns the index of the maximum value for mpg variable, and attaching that with the empty cars variable displays the row with the maximum value for mileage. You can see that Toyota Corolla has the maximum mileage in the given set of cars. Step 10. Similarly, the row with the minimum value can be found using the which.min function. Let us find the lightest car in the given set of cars. Type empty cars of which.min of empty cars $WT and a comma. We now know that the Lotus Europa is the lightest of the cars. Step 11. The commands mentioned now can thus be used to find the maximum or minimum of any variable and the corresponding car data. You are encouraged to try different combinations to get meaningful insights. Step 12. As a final exploration technique, let us try the aggregate function. Suppose we would like to know the average mileage of cars that have 3 gears. We will use the aggregate function to aggregate the mpg variable by the variable gear, and the aggregation function would be average. Type aggregate of mpg tilde gear, comma, data equals empty cars, comma, fun equals mean, and press enter. The output consists of 2 columns, the number of gears and the mean of the mileages. We can infer that the cars with 3 gears have a mileage of 16 on average. The cars with 4 gears are the best in terms of mileage, giving the highest average mileage. The aggregate function can similarly be used to find the average speed of manual and automatic transmission vehicles, and so on. Following mathematical exploration techniques, we will now visualize data and try to support the inferences made through the earlier commands. Step 1. Let us start with a scatter plot that includes all the factors in the dataset being plotted against each other. Type plot of my data and hit enter. The new window shows a plot with all the variables plotted against every other variable in the dataset. Step 2. But this gives a very generic plot of all the variables, and it is hard to make any useful inferences from this plot. Suppose we want to know how the horsepower is related to the displacement. Let us use the plot function with the formula HP tilde disp to get the corresponding plot. We can infer from the scatter plot that the horsepower increases even though gradually as the displacement increases. You can see one data point that might occur as an outlier. The horsepower is quite high for a large displacement vehicle. This shows that there are other factors that have an effect on the horsepower. Step 3. Let us perform a similar plot for the number of cylinders versus the mileage. The formula for the plot function will be mpg tilde sil. You can see the number of cylinders are 4, 6, and 8. And as the number of cylinders increases, the mileage decreases, and the effect is quite visible. This plotting can be done across every combination of variables, and such inferences can be obtained. Though it is statistically possible to create plots for any 2 variables, during a case study, it is advised to understand the data before plotting them. For example, A plot of employee ID versus age in an employee database will work in R, but will not help the researcher in getting any meaningful insights since they are logically unrelated. Step 4. Let's work on the categorical variables. We have the AM variable, which has two values, 0 for automatic and 1 for manual transmissions. The summary statistic will show us the number of automatic and manual cars. But if we have thousands of data, it will be difficult to obtain a ratio of the two categories. You can graphically view the ratio using the pie charts, as seen in the previous lessons. We will use the pie function. We will create a table of the AM variable using table of empty cars $AM and pass it as an argument to the pie function. From the chart, it is seen that almost 60% roughly are automatic cars in this case. Step 5. Okay, now let us do a very simple pie chart plotting. Let us consider plot for AM data. AM is for automatic or manual property of cars. So, if it's needed to find if number of automatic given by 1 is more or less than number of manual, this simple plot can be done. So type some name of the data frame, say auto, to extract the data of AM in the dataset of empty cars. So type equals empty cars $AM. Then it's needed to make a table. So make another data frame to assign table for auto. Then for the pie plot, type pie of matic. And now, from the pie plot, it's evident that the number of manual is more than the number of automatic. Step 6. Similarly, create a pie chart for the number of gears. Here, the table should be created for empty cars $gear and passed the pie function. We can infer that almost half of the cars have 3 gears. The other half is distributed between 4 and 5 geared automobiles, with the cars having 5 gears being the least number. Step 7. The continuous variables can be viewed using box plots, as we have seen earlier. Let us create a box plot of the horsepower, grouped by the number of cylinders. The formula for box plot will hence be HP tilde sil, and mention data equals empty cars and pass them as arguments for the box plot function. You can see that the horsepower increases as the number of cylinders increase. For cars with 8 cylinders, there is a lot of variation, as can be seen from the wider box and whiskers for the plot. Out of the 3, cars with 6 cylinders have very less variation, though there seems to be an outlier as seen by the dot in the graph. It can also be seen that the median or horsepower for cars with 4 and 6 cylinders do not differ much. Step 8. Let us look at a few bar plots and try to make sense of the graphs. Suppose you want to know the number of cars grouped by the number of gears. To know this, use table of empty cars $gear to create a table of the counts, and pass this as an argument to the bar plot function. From the plot, we can find that maximum number of cars, that is, 15 cars have 3 gears, and 12 cars have 4 gears, and 5 cars have 5 gears. Similarly, this can be done for the number of cylinders. Type bar plot of table of empty cars $sil to view the plot. Here we can see that most cars in our data set have 8 cylinders, and the least cars have 6 cylinders. This inference from the bar plot can be done for all discrete grouping factors. Step 9. As a final descriptive statistic, let us make a histogram plot for the horsepower of the cars. To display the histogram, type hist of empty cars $HP. The histogram divides the horsepower into buckets of 50 units, starting at 50 and ending at 350, thus having 6 bars. we can see that most cars fall into the 100 to 150 horsepower range, and only 2 cars have horsepower of above 250. This concludes the case study on descriptive statistics using R. In the next slide, we will discuss, let's look at the function to test the correlation between 2 variables. Correlation is a class of statistical relationship between 2 variables that forms any form of dependence. For example, is there a correlation between the height of parents and their offspring? In the example given, we try to find if there is a correlation between the sepal length and width of a flower. In R, correlation can be calculated using the core.test function. By default, the function calculates the Pearson's correlation coefficient. Let's look at how to interpret the results. The output shows the correlation method used and the data. The important output for this test is the p-value, which is calculated using the t-statistics and degrees of freedom. As seen in earlier chapters, if the p-value is less than 0.05, we can conclude that the null hypothesis is rejected. That is, there is no correlation between the 2 variables. The correlation coefficient is given as 0.1175698. This means there might be a negative correlation between the 2 variables. But since the p-value is quite high, we conclude that the result is not significant. That is, the correlation is almost 0. Next, we will look at a video to understand correlation using R. In this video, we perform a correlation test on 2 variables on a dataset to ascertain the significance of the relation and values of the variables. We will use the anorexia dataset from the mass package for the correlation. Load the package by typing library of mass. Specify mass in capital letters. We will use 2 variables of the dataset to perform the test. That is, pre-WT and post-WT. Run the command core.test of pre-WT and post-WT separated by a comma. The output shows name of the test, that is, Pearson's product moment correlation, in this case followed by the t-value, degrees of freedom, and the p-value. Then it tells you about the alternate hypothesis, which in our case is the true correlation is not equal to 0. Next it shows the 95% confidence values of the correlation, and finally, the mean of the correlation values. In the next slide, we will look at a correlation case study. In this slide, let's look at a case study to illustrate the concept of correlation. The business case we have chosen is about an ice cream company which maintains a database containing total sales per day and the corresponding temperature each day. Given this data for a period of 1 week, the management wants to find whether temperatures is a factor that causes difference in their sales. Looking at our data set, we can infer that there are 2 variables, sales and temperature. Here, sales represents the value of total sales that happens in the ice cream company each day. And temperature represents the temperature that is being recorded for the corresponding day, measured in Celsius. We will be using correlation to check whether there is any relationship between sales and temperature for this company. and the following video will walk you through the process. Firstly, save the data into a CSV file. Step 1. Import the file in R. As seen earlier, use the read.csv command to read the CSV file with the file name given as arguments. Step 2. Save the dataset in R as My Data. Step 3. To check for the data in the dataset, type My Data and press Enter. The data will be displayed, and you can check if the data has been stored properly. The data will have 7 entries across 2 columns. Step 4. Before working on My Data, attach the dataset My Data to the session by typing Attach of My Data. Step 5. The correlation coefficient is now determined by using the command core.test. We need to supply the variables as arguments, so type sales, comma, temperature within parentheses and hit Enter. Step 6. The correlation result is displayed. It can be inferred that the Pearson's product moment correlation test has been performed. The test can be changed by using the method attribute. The t-value for these 2 variables is calculated as 6.6333. The degrees of freedom is 5, and the p-value is given as 0.001173. The basic alternative hypothesis is displayed, and the 95% confidence interval is calculated and displayed. Pearson's correlation coefficient, RHO, is displayed in the last line and equals 0.9476071. From the earlier lessons, we know that a positive sign in the correlation coefficient implies they both are positively correlated. That is, an increase in temperature leads to an increase in sales. The value is close to 1, which suggests that the association between the 2 variables is very strong. In the next slide, we will discuss analysis of variance. ANOVA is used to compare the means between different groups. Here, we show a simple example of one way, ANOVA. To illustrate this, we use the insect sprays dataset. This data contains the insect count after using 6 different sprays. Here, the null hypothesis would be that there is no difference in using different sprays. AOV takes the first attribute as dependent variable and independent variable, separated by tilde. Here it is AOV of count spray. The data attribute specifies where the data is to be taken from. After fitting the AOV model, the summary function is used to display the result. It can be seen that the p-value, that is the last column, is lesser than 2e minus 16, which is the least positive number represented by R. Since p-value is almost 0, we can reject the null hypothesis, and thus the inference is that there are differences in results on using different insect sprays. Next, we will look at a video that shows how to perform ANOVA in R. Now, let us perform ANOVA in R using the insect spray dataset. For ANOVA, a model needs to be fitted where we have to decide on a target variable and one or more independent variables. Step 1. In our case, let's take count as the target variable and spray as the independent variable. Step 2. For fitting the model, use the AOV function and save it in a user-defined model name, say fit. So fit equals AOV of count tilde spray followed by passing the data, that is insect spray, separated by a comma. Step 3. To check the model details, run the command fit. Step 4. The result shows a table containing 5 major columns that are in order: degree of freedom, sum of squares, mean squared error, f-value, and p-value for each of the independent variables used in the model. Finally, the significance of the variables can be checked from the p-value in the table, and the important variables can then be used for further advanced modeling. In the next slide, we will look at a case study. Let's look at a case study for better understanding of ANOVA. A pharmaceutical company has tested 3 formulations of a body pain medication for athletes. 27 volunteers were selected, and they were split into 3 random groups. 9 members were assigned randomly to each of the medications. The athletes were instructed to take the medication while experiencing body pain and then report the pain on a scale of 1 to 10, 10 being too much of pain. Here, the table shows the pain rating for each athlete across each medication. The question the company wants to answer is there a significant difference in the effect of the different medications? Since there are more than 2 different groups, we will use analysis of variance to test the significant differences between means of all 3 medications. And the following video will walk you through the process. To start with, save the data into a CSV file. Step 1. Import the file into R. Let's name the file as MyData. To read the file, type MyData equals read.csv of the file name within brackets. Make sure the file is in the current working directory, and if not, type the absolute path of the file with forward slashes to separate the directories. Step 2. Check if the data has been imported by typing MyData to display all the data. Alternatively, you can use head of MyData to display the first 6 rows. Step 3. To apply R's ANOVA function, the data has to be in a single vector format. To do so, let us first convert the 3 columns of data into a single vector. Use the C function to do the conversion. After attaching the data to this session, that is, using attach of MyData, type C of med_1, med_2, med_3. Save it in a variable. Let us name it pain rating. Now type pain rating to see if the vector has been properly stored. Step 4. Now the medication type for each entry data needs to be specified. Create a vector that consists of the value medication 1 for the first 9 entries, medication 2 for the next 9, and medication 3 for the last 9 entries. Let us save it in a variable called types. The rep function can be used to repeat a given string for a given number of times. For example, rep of medication 1, 9 will create a vector that has medication 1 repeated 9 times. To create the types vector, type C of rep of medication 1, 9, rep of medication 2, 9, rep of medication 3, 9. You can now type types on the prompt to check if the vector has been created properly. Step 5. Finally, a data frame has to be created that contains the medication type and its corresponding pain rating. Let us save the data frame in a variable called body pain rating. Type body pain rating equals data.frame of pain rating, comma, types. You can see the data frame by typing body pain rating to view the whole data frame. You can notice that this frame contains two columns, pain rating and types, and consists of 27 rows. Now we have the data frame ready. Step 6. Before using ANOVA, let us visualize the data in a graphical format. We will be using the plot function to plot the ratings as a function of the medication type. Type the command plot of pain rating, tilde, types, comma, data equals body pain rating and hit enter. The box plot of the ratings is displayed in a new window. Note that there is an outlier on the medication 2 rating entries. It can also be noted that the median for medications 2 and 3 are the same, and the median for medication 1 is significantly lower than the other two. Let us now get back to the command prompt. Step 7. As seen in the earlier video, the AOV function is used to perform analysis of variances on the data. The formula for AOV function should be pain rating tilde types, which implies that the grouping is done per the types column. Let us save the result into a variable named ANOVA result. Type ANOVA result equals AOV of pain rating tilde types, comma, data equals body pain rating. To view the results, we use the summary function. Type summary of ANOVA results to see the results of the test. Step 8. From the previous results, you can see that the value of F statistic is 11.91, with a p-value that is equal to 0.003. Since the p-value is significantly lower than the standard value of 0.05, we can infer that the null hypothesis needs to be rejected. In the context of this study, we can conclude that different medication formulations have different impacts on the pain rating for athletes. In the next slide, we will look at the squared test is used to calculate the goodness of a particular fit. It compares the observed values against expected values obtained from a null hypothesis. Here, we try to test the sepal length for goodness of fit. The low p-value suggests we can reject the null hypothesis. We will now look at a video to understand how to perform a chi-squared test in R. Now we go about doing the chi-square test. For this test, we need a categorical data set, and R has that kind of data pre-installed in it. The data set is called hair eye color. Step 1. Call that data set using the data function. Run the data of hair eye color, and it becomes active in the workspace. Step 2. To handle the data more efficiently, save it in a user-defined variable, say, my data, and put it in a data frame. Step 3. Then do a head of my data to have a look at the data set. Step 4. Just to make things a little more flexible, attach the newly made data set, my data, to the workspace. Step 5. After clarifying the structure of the data set, do the chi-square test. Step 6. Next, for doing the chi-square test, we select two variables from the data set. Say hair and eye, and run the command kisk.test of hair, I. After running the test, we find that these two variables are not at all related and have no significance between each other, suggested by the p-value, which is equal to 1. Step 7. Hence, we move on to choose another set of variables and take hair and freak for the test. This time, we find there is some amount of significance between these two variables, suggested by the p-value, which is equal to 0.06, very close to the 0.05 significance level, which is generally used as benchmark. In the next slide, we will look at a case study. Pairwise t-tests are used to check if there is any difference in paired values. For example, marks obtained by a student before and after a training. To illustrate this, the anorexia dataset from the MASS package is used. The data contains pre-treatment and post-treatment weights of patients. To implement it in R, type t.test of prut, post WT, paired equals true. The first two attributes are the features to be compared, and the attribute paired equals true specifies that it is pairwise t-test. The low p-value suggests that the null hypothesis can be rejected. That is, there is a difference between the weights before and after treatment. In the next slide, we will look at independent t-test. The independent t-tests are used in comparing two values where the value of one variable is not directly related to the other variable. For example, marks of students in two different schools. Here we implement a t-test on the sepal length and sepal width of the iris data set. From the result, it can be seen that the p-value is almost 0, and hence the null hypothesis that there is no relation can be rejected. Now we will look at a video that shows how to perform t-tests using R. Next, we try to see how to do t-tests in R. Starting off with the one-sample t-test, use the anorexia dataset for this purpose. Step 1. Choose any variable of the dataset to perform the test, say pre-WT. Step 2. Run the command t.test of pre-WT and pass the parameter mu equals 3 separated by a comma. The mu parameter corresponds to the null hypothesis. Step 3. The output shows name of the test, which is one sample t-test, followed by the t-value, degrees of freedom, and the p-value. Step 4. Then it tells you about the alternate hypothesis, which in our case is the true mean is not equal to 3, since we passed 3 as the value for the mu parameter in our test. Step 5. Next it shows the 95% confidence values of the variable, and finally the mean of the values of the variable. Next we do the independent t-test, also known as the two-sample t-test. Step 1. Choose any two variables of the dataset to perform the test, say pre-WT and post-WT. Step 2. Run the command t.test of pre-WT and post-WT separated by a comma. Step 3. The output shows name of the test, that is, Welch 2 sample t-test, followed by the t-value, degrees of freedom, and the p-value. Step 4. Then it tells you about the alternate hypothesis, which in our case is true difference in means is not equal to 0. Step 5. Next it shows the 95% confidence value of the combinations of the variables, and finally the means of the values of the variables. Now we will do the pairwise t-test. Step 1. Choose any two variables of the data set to perform the test, say pre-WT and post-WT. Step 2. Run the command t.test of pre-WT and post-WT separated by a comma followed by the paired parameter, which must be entered as equal to true. So to tell the test that you are trying to do a pairwise test. Step 3. The output shows name of the test, that is, paired t-test, followed by t-value, degrees of freedom, and the p-value. Step 4. Then it tells you about the alternate hypothesis, which in our case is the true difference in means is not equal to 0. Step 5. Next it shows the 95% confidence values of the combinations of the variables, and finally the mean of the difference in corresponding values of the variables. In the next slide, we will look at a case study. A construction company took a project of building luxury residential apartments in Phoenix City. The project head, Andrew, decided to make an analysis on other residential apartment constructions nearby Phoenix in order to avoid management difficulties and to easily compete with their competitors. So he asked his colleagues to collect all relevant information that helps him in finding useful insights. He wants to find all the business insights possible so that he can compete with all other competitors and also avoid taking much risk in terms of decision-making and investments. His colleagues started collecting relevant data. For this, he did a survey of various construction sites in and around the locality. The final data that he collected contained information on 12 variables: ID, local price, bathrooms count, area per square feet, living space per square feet, garage count, rooms count, bedrooms count, age in years, selling price, material, and level. Let us assume that you are the analytics expert in the company and have been assigned the task of working with the data to get insights. Now, we have the data gathered and ready for analysis. The first step that needs to be followed is to import the data into R. For the purpose of analysis and easier access to the data, we will store this data in a time frame and name this data frame as MyData. So, type MyData equals read.csv and give the path for the file. We will see the first 6 data entries and check if we have chosen the correct data set. To do so, we typed head of MyData and the first 6 rows are displayed. Now, let us jump into the analysis. The first thing we do to start off with analysis is descriptive statistics of the data set. We get this in R by typing summary of MyData. Now we can see the summarized information of each and every variable in the data set. We have the minimum value, the maximum value, and first and third quartile value, the median and the mean value given for each of the variables. Let's see for the bedrooms count variable. We see that the apartments have a minimum of 0 bedrooms, which might correspond to studio apartments, and a maximum of 7 bedrooms. The median value is 3, specifying that apartments with 3 bedrooms are the most common. The first quartile as we know, is the middle value between the smallest number and the median of the data set. For bedrooms, this value is 3. Similarly, the third quartile is the middle value between the median and the highest value in the data set. For the bedroom count variable, this statistic is equal to 4. The mean is almost 3, again showing that the apartments in this locality generally have 3 bedrooms. The individual summaries can be obtained by using the $sign, as we have already discussed. If we observe the summary data, we will find that material and level don't have the usual statistics like the quartiles, mean or median value given for them. They are instead classified into their types and the number of occurrences of each type. We can see that most houses are brick houses, having the highest count, and aluminum wood houses are the least common. From the level variable, we can see that a majority of the houses are 2-storied. There are only 3 ranches and 7 split-level apartments, and the rest are all 2-storied. So constructing a 2-storied apartment would be a very safe bet in this neighborhood. However, obtaining the summary of my data doesn't give us information of other important statistical terms, like the standard deviation, variance, etc. This statistical information is important to make further decisions and for analysis. Though R has individual statistic functions like the SD, var functions to obtain these values, we will use a library package to obtain all the statistics. R has a package named Pastix that can be installed by using the install.packages function and included in the current working session by the library function. We use the stat.desc function to obtain a comprehensive statistical summary of the data. So we type stat.desc of the data frame. That is, my data in this case study. And here we can see statistics like the number of values, number of nulls, number of NA values, the range of values in the variable, the sum of all the values, the standard error of the values from the mean, the confidence interval mean for a 95% confidence level, the variance value, the standard deviation value, and the coefficient of variance. Let us look into the statistical description for a particular variance, say garage count, and understand these factors. The first row, nbr.val, give the number of values, that is, 57. The nbr.null value is 6, which means there are totally 6 records in our data set that have a garage count of 0. Then nbr.na shows a value of 0, which means that there are no not applicable situations. The next row is minimum value, and it displays 0. So that means there are houses with 0 or no garages. The max column shows a value of 2. So their maximum number of garages in an apartment is 2. Next, we can see the range. Range is nothing but the difference between maximum and minimum value. We can say that there are a 0 to 2 garages in the apartments belonging to this locality. Next factor is sum, and the value displayed is 73. So in this locality, there are 73 garages. The next is median, and its value is 1 for garage count. That is, most apartments have 1 garage. We have a mean value of 1.28, however. We cannot take the literal interpretation, since the number of garages must be a whole number. The next factor is standard error of mean. It is usually estimated by dividing the sample estimate of the population standard deviation by the square root of the sample size. Next factor here is confidence interval mean. When we compute a confidence interval on the mean, we compute the mean of a sample in order to estimate the mean of the population. For our example, the standard error and confidence interval mean do not add much meaning to the interpretations, so we ignore these values. To understand these values, let us analyze the selling price variable of our data set. The selling price of apartments in the locality varies from $13 million to $84 million. The standard error mean here is 1.69 million. The confidence interval mean for a 95% value is twice the standard error. That is 3.4 million. We know that we are working on a sample data set. The mean of the sample data of apartments is around 34 million. What the confidence interval tells us is that we can say with 95% confidence that the mean of the population will vary between 34 plus or minus 1.69 million. That is 32.31 to 35.69 million. Next, we have the variance of the selling price. The variance is quite high, as you can see here, 164.38. The standard deviation is 12.8 million. This logically makes sense as we have our data ranging from studio apartments to partial apartments with 6 bedrooms. And the prices of these apartments will have a large variation. And the last factor we can see is coefficient of variance. This shows the percentage of variation from the mean. For the selling price, it gives a value of 0.37. That is, there is a 37% variation of values around the mean. Let us view the selling price data in a histogram. Type hist of selling price. From the results, we see that there are buckets of 10 to 90 million, increasing by 10 million each. Most of the houses are sold in the $20 to $40 million range, and there are no houses sold in the $60 to $80 million range. There are 2 apartments sold above $80 million. We are interested in knowing what is unique about these apartments. To view just these 2 records, we will subset the data. Type my data of my data dollar selling price greater than 80 and comma. 2 records are displayed. We know that wooden houses generally have a higher selling price. Also, the count of rooms is pretty high for these 2 apartments. The first data has a very high age value and might have sold higher because of its vintage value. Now, let us find the variations in selling price according to their number of rooms, number of bedrooms, etc. As seen in the lesson, we will use the aggregate function for this purpose. We attach the data frame to the session by attach of my data. Now, let us aggregate first by number of bedrooms. Type aggregate of selling price tilde bedrooms count and specify function as mean. We get the corresponding average selling price for each number of bedrooms. We can see a steady increase in selling price as the bedroom count increases. From 1 to 2 bedrooms and 4 to 5 bedrooms, there is a jump in the selling prices. Apartments with 3 or 4 bedrooms have almost the same average selling price. The apartments with 5 bedrooms have the highest selling price, so apartments and people in this locality are willing to pay more for apartments with 5 bedrooms. We should also remember that both apartments that sold highest had 5 bedrooms, and thus the average results might not be the right statistic due to the presence of outliers. Let us do a similar check on the selling price according to the garage count. There is a huge difference between the average selling prices of apartments with no garages and 2 garages. So adding a garage might be beneficial in increasing the selling price. The next thing that we would be doing with the data set is to see which factor is actually affecting the selling price of the apartments. That is, whether the pricing is affected by the house material, or the number of rooms, or the living space per square feet, etc. So, to find out the variables responsible for pricing, we will do correlation. The correlation will tell us about how much the variables correlate with each other and also with respect to the pricing factor of the houses. Here, another thing to keep in mind is that in our data set, we even have variables which are categorical. As we already know, correlation can only be performed on numerical values and cannot be performed on the other values. So how do we go about solving the issue with the categorical variables? One way to go about this is to manually select the numerical data. There is an easier option too. That is, we can specify an attribute to the correlation function which states to select only the numeric values. The function lapley of x comma function f returns a list of same length of x. After applying the function f on each of the data item, we will use this function with the is.numeric function to remove non-numeric values. So, let's type core of my data of unlist of lapley of my data common is.numeric. So now we can see the correlated value of every numeric variable with every other numeric variable in the dataset apart from the material and level variables. Let's check which of the variables has the highest correlation with the variable selling price. Looking at the selling price column, or row, we see that the local price has the highest correlation value of 0.79. The living space per square feet variable is a very close second, having a correlation of 0.789 with the selling price. So, the selling price is strongly correlated with the local price and the living space of the apartment, as suggested by the correlation of almost 80%. We can see that age in years has a negative correlation with the selling price with a value of minus 0.21. Thought the correlation coefficient is quite low? We can see that an increase in the age for apartments tend to decrease its market value. Performing correlation for all the variables against all the other variables is more advantageous as it compares all the variables and helps us in getting insights which might not be visible by just looking at the data. For example, we can see that garage count has a mild correlation with almost all variables. So the number of garages to be built for an apartment is quite independent of the number of rooms or bedrooms or the living space. However, the presence of a garage tends to have an increase in the selling price, as can be seen from a correlation of 0.4 with the selling price. Now suppose we don't need to correlate entire table. Need to test the correlation between two variables. In such cases, we can just type core.test and mention the two variables whose correlation we want to know. Suppose we want to know how much the number of rooms is related to the price of a house. So to correlate selling price with number of rooms, we type core.test of rooms count, comma, selling price. Here we can see the results to be 0.55. From this value, we can understand that there is about 54% relationship between the number of room counts and selling price. Also, the p-value is very less, which supports the hypothesis that the two variables are related. The next test we will perform on the data is ANOVA, analysis of variance, as we have seen in a collection of statistical models used to analyze the differences between group means and their associated procedures. The calculations of ANOVA can be characterized as computing a number of means and variances, dividing two variances and comparing the ratio to a handbook value to determine statistical significance. Here we shall perform ANOVA on selling price with two categorical variables we have in the data set. Let us first test the means per the level variable and store it in a variable called fit. So we type fit equals to AOV of selling price tilde level data equals my data. Now type fit and we can see the ANOVA result. The first factor we can see is sum of squares. It is the deviations from the sample mean. From the ANOVA result between selling price and level, the sum of squares value is 43, and the residuals is 9,162. The next factor, number of degrees of freedom, is the number of values in the final calculation of a statistic that are free to vary. In this case, degree of freedom of level is 2, and residuals are 54. Next type summary of fit, we get other parameters like the mean squared value, F statistic, and P value. The very low value of F statistic and higher value of P value imply that we cannot reject the null hypothesis. The obtained P value is 0.8, quite high compared to the standard value of 0.05. When we analyze the levels variables, we see that most of the apartments fall in the two-story category. This kind of skewness affects the ANOVA since their number of observations in each group is highly unequal. Let us view this graphically by using the plot function. Type plot of selling price tilde level gives us a box plot of the selling prices for various values of levels. We can see that two-story and ranch apartments have a high variance, whereas split-level prices vary very little. Also, for two-story, there are two outliers in the data. A similar ANOVA can be done with material and selling price too. So type fit equals AOV of selling price tilde material, comma, data equals my data, and we can see the ANOVA results for material. We see the sum of squares value for material is 637.88. Residuals value 8,567.61. The degrees of freedom of material is 3, and residuals is 53. Next, we type summary of fit, and we can see the other parameters. Similarly here, even though the F value is comparatively higher, the P value is higher than the standard value, and hence we cannot reject the null hypothesis. We will view a similar plot as earlier by typing plot of selling price tilde material. The apartments constructed with wood have a comparatively lesser variance. There are two outliers in this graph as well, and correspond to brick wood and wood categories. Here, we have performed a comprehensive descriptive statistics on the data and some inferential statistics depending on the data we have at hand. It is very important to note that the type of tests and the statistics that we use depend entirely on the business need and the type of data we have. It is common in analytics to be sidelined from the purpose of the research or analysis by applying various tests on the given data. Through this case study, we have provided an example of when to apply which statistic and where to apply different tests of significance to arrive at meaningful insights. Let's look at an experiment to understand the use of t-tests. A researcher studying the effect of a drug on the growth of tumors wishes to find if the drug reduces the growth of tumors. The researcher obtains mice with tumors and divides them into two groups. One group of mice was injected with the drug, and the other group was used as the control group. After 1 week, the tumors were weighed again, and the results were noted as follows. The research question is, does the drug reduce the tumor size? In the given table, we can see the tumor size of mice treated with the drug and the tumor size of the mice belonging to the control group. Since these two belong to two different groups of mice and have no dependencies with each other, we will use independent t-tests. Let's recall the assumptions for independent t-tests. The samples are random. The measured values on a continuous scale. The independent variable is measured on two groups or categories. That is, in our case, the experiment and the control group. The observations are independent and follow an almost normal distribution. There is homogeneity of variations. And lastly, there should not be any significant outliers. Since our data adheres to all the above assumptions, we can continue with the significance test. The researcher wants to know if the use of the drug decreases the tumor size. Hence, it corresponds to a one-tailed hypothesis test. Remember that two-sided hypothesis tests would be used when the research question is whether there is a difference in tumor size as the result of the drug. In the video, we will look at how to perform a t-test for this study and if the hypothesis is proved or rejected. Let's start by loading the dataset into R. Step 1. Make sure the working directory in R is set to the directory with the data file, using the getwd and setwd commands. Step 2. Create a data frame tumor data and read the file using the read.csv command. The argument to the command is the name of the CSV file with the extension .csv. Step 3. As seen earlier, the head command displays the first 6 rows of the data. Type head of tumor data to display the first 6 rows of the data. Step 4. Before planning the t-test, let us visualize the data using box plots. Type box plot of tumor data to create box plots of the 2 columns. The plots are created and displayed in a new window. Here you can see that the median of tumor size for mice not treated with the drug is higher than the mice treated with the drug. Also, the quartiles or deviations from the median are higher for the control group. Step 5. Next, let us perform the t-test to find whether the drug has an effect on the tumor size. As shown in the previous video, the t-test command is used to perform the t-test. Before performing the test, let us attach the data frame by typing the command attach of tumor data. Now type t.test of treated with drug, comma, not treated with drug, comma, alternative equals L. The alternative equal to L is used to specify that the test is a one-sided test. And we are concerned about the lower tail, that is, if the tumor size is lesser. On hitting enter, the test results are displayed. The t-value is given as minus 2.0643, and the degrees of freedom is 13.651. Using these two values, the p-value is generated as 0.02927. The next columns display the 95% confidence interval, that is, minus infinity to minus 0.009. The sample estimates are displayed below. The mean of x and the mean of y. X and y are used to denote the 2 columns. Here we can see that the mean of tumor size for the experiment group is 0.675, and the mean of tumor size for the control group is 0.742. The null hypothesis for this case study is that there is no difference between the means of the 2 groups. Correspondingly, the alternative hypothesis states that the true difference in means is less than 0. With a significance value alpha of 0.05, we can reject the null hypothesis, since the p-value is less than 0.05. Thus, we can conclude that the drug has an effect of the size on tumor in mice, and the tumor size reduces as an effect of the drug. With this, we complete the concepts of basic analytic techniques. Now, we will look at a business case to illustrate the concepts that we have learned in this lesson. Let's quickly summarize what we have learned in this lesson. We have discussed a basic introduction to R, data exploration using R, data visualizations in R, pie charts, bar plots, box plots, histogram, diagnostic analytics using R, chi-squared test, t-tests, analysis of variance. The quiz section will help you check your understanding of the concepts covered. This includes Lesson 3, the Business Analytics Foundation with R Tools course offered by SimpliLearn. Thank you for your attention. Please continue your learning with Lesson 4 of this course.